Okay, let's talk about today, introduction to hypothesis testing. So this is a pretty heavy chapter when it comes to all the different aspects. So it's really important that we spend some time talking about and introducing hypothesis testing. And this is no small section. This is really important that you practice setting up the hypothesis test because the setup determines the test. So if you do not set it up properly, then you will find that you will run the wrong test, and obviously everything after that is not correct. What the heck is a hypothesis test? So a hypothesis test is a process that uses sample statistics to test a claim about the value of a population parameter. For example, consider a manufacturer that advertises its new hybrid car has a mean gas mileage of 50 miles per gallon. If you suspect that the mean mileage is not 50 miles per gallon, how could you show that the advertisement is false? Okay, so think about it. Here we are, we have this advertisement, and we're like, you know what? I really don't believe that. I've had a hybrid vehicle for I don't know how long, and I only get 30 miles per gallon. So I'm in disbelief that they made one that can can do 50 miles per gallon. And I am actually not speaking from experience. So just saying, let's say somebody was thinking this. So what would happen is they would go to this dealership or the manufacturer. They would, let's say, collect 100 hybrid vehicle cars that are all stated to get 50 miles per gallon. They fill up the gas tank to absolute full. And in order to keep consistent, really, it should be one driver driving all 100 of these vehicles from full tank to empty. And then they would calculate the miles per gallon for each of the 100 vehicles driven. Then you take that, you add all the 100 together and divide by 100 to get your X bar, your sample mean. Now, what the hypothesis test will do is it will take that sample mean and it will compare it to the hypothesized mean, 50 miles per gallon, and it will determine whether the difference is significant or not. If it's significant, then we will say, you know what, we don't believe the manufacturer because our test shows that the average miles per gallon is significantly different. But if the test determines that the values are not significantly different, then we would say, you know what, we have no evidence to discredit the manufacturer's claim. So a statistical hypothesis, you probably have heard of the word hypothesis from like the scientific method from high school or college classes. But a statistical hypothesis is a statement about a population parameter, really important. Parameters make it into the hypotheses, not statistics. So do not put X bar, P hat, S in a hypothesis. Carefully state a pair of hypotheses, one that represents the claim and the other one is the complement. When one of the hypotheses is false, the other must be true. That is why we need to set up a perfect complementary situation so that we know something about the other hypothesis that the test cannot test for. It only tests for the null. Either hypothesis, the null hypothesis or the alternative, may represent the original claim. So the claim is not purview to the null only or the alternative only. It really depends on the wording of the problem, and that will make more sense as we progress through this section. So the null hypothesis, which is denoted by H sub 0, which is really called H naught, and you can see the spelling down here, like naughty, is a statistical hypothesis that contains a statement of equality. So what's important about the null is that it has the equal sign. So any one of these three symbols all have equal signs and they all need to be in the null hypothesis. This has to do with the way the test is designed. The test is designed to test the equal sign, to test the null. It doesn't matter what the claim is. The claim is secondary to the test. It's about the null hypothesis. The alternative denoted by H sub A, is the complement of the null. It is a statement that must be true if the null is false, and it contains the complementary symbols. So notice if we have less than or equal to, the complement would be greater than. And if we have a strictly equal to, the complement would be not equal to. And a greater than or equal to, the complement would be less than. And the only way that this works is if both hypotheses have the same number in them, because we are trying to cover the entire number line and not leave not one little smidgen out in order to build that complement. So here are your three possible setups. You have the null and the alternative. And let's say we're talking about the mean. So we have mu is less than or equal some claimed value, and mu is greater than that same exact value, and the other two cases. Okay, so the only thing that can be here is either mu p, the population parameter, or sigma, the population standard deviation. Now, in this course, I really do not focus on sigma and hypothesis testing. I do that in the advanced stats course. So we're only worried about means and proportions. This slide is really helpful, and I strongly recommend you consider printing it out for your notes, because it does help with translating English into math, which we all know can be a struggle. When it comes to inequalities and translating, I like to think of money, because that tends to help me translate what on earth I'm talking about. So for example, let's say that a problem read that I have at most, or the hybrid vehicle has at most 50 miles per gallon. And I'm like, at most, was that a less than or equal to, a greater than or equal to? And if I can't figure it out, one, this chart is very helpful. So this is the null at most less than or equal to, null less than or equal to. Or I could think about money. So if I told myself I have at most $100 in my pocket, well, that means that I don't have more than $100. I either have $100 or less. And for some reason, when we talk about money, because money's important to us to pay our damn bills, it's easier for me to translate inequality statements, because I know what I'm talking about when I mention my money. So for example, stating the null and alternative hypothesis, let's try a couple examples. So a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. This one can be a little tricky because of this wording. So at least, many students, when they first try this one, they get it wrong because they see the words at least and they think, oh, okay, so I have at least $50 in my pocket. That means I know I have 50 and I might have more. So that's greater than or equal to, and they go with that. But be careful. This is describing the population, the target population. We're talking about students who take at least one extracurricular activity. That is not the claim. That is the target population description. The claim is that the proportion of these students is 61%, and is translates to an equal sign. So I'm going to label my null and my alternative, and these are always should be labeled. And I see that I'm talking about proportions, so the population parameter for proportions is P. Okay, so that's what you always label, you always identify your parameter, and then you translate the claim. Now the claim is an equal sign, and I remember that the equal sign must go in the null hypothesis. So I'm going to put equals to 0.61. Notice it's not the percentage because we're talking about proportions. Proportions need to be in decimal form. And it's always good habit to label the claim. And this will make more sense when we start doing an actual hypothesis test in the next couple sections, because you're going to see that the test, again, is testing the null and the claim is secondary, but you have to know which hypothesis is the claim in order to actually make that secondary, the secondary conclusion. So now I have to build the alternative since it's the hypothesis without the claim. And I need to just make it the opposite of an equal sign. So if this null is an equal sign, then the opposite is not equal to. Always use the same parameter value. Let's try this one. So this one says that a car dealership announces that the mean time for an oil change is less than 15 minutes. So I look, and again, I'm going to start by labeling because I know regardless I need labels. I need null and alternative labels. I'm then going to identify my population parameter. So I look in here and I see the word mean. So that's going to be mu. And then I find the claim. Now the claim is less than 15 minutes, and that's a strictly less than. Ooh. And a less than does not have an equal sign, which means it doesn't go in the null. Okay, a less than will go in the alternative. So I'm going to put less than 15 and I'm going to label the claim. So this time the claim, by the wording of the problem, because the wording did not include an equal sign, is written in the alternative. And now the null becomes the complement. So the complement of a less than is greater than or equal to 15. Okay, right now, notice we're just practicing the setup. We will worry about the test and future sections, but I'm telling you this setup is so important. This alternative hypothesis determines the test you do, which then directly affects the results. Example 3. A company advertises that the mean life of its furnaces is more than 18 years. So again, I'm going to set up my null and my alternative. I identify the population parameter as a mu because it mentioned the word mean, or it can mention the word average. I'm then going to translate the claim more than 18 years. More than does not use an equal sign, so I'm going to the alternative and label the claim, and then build the complement, which is the opposite, less than or equal to 18. So if we take a look at these as a number line, the first example was an equal to hypothesis and a not equal to. So exactly equal to 0.61 and not equal to 0.61 is everything else. Notice that the entire number line is shaded, meaning that when I find out if the null is true or false, it is very clear that the alternative is the opposite. It's if the null was true, then the alternative is false and vice versa. Okay, our second example, we were less than 15, so the blue does not include 15. Notice the 15 is included for the null because that was greater than or equal to. And similar situation for example 3. Now, another thing that we need to keep in mind is the types of errors. So no matter which hypothesis represents the claim, always begin the hypothesis test assuming that the equality condition in the null hypothesis is true. So when you perform a hypothesis test, one of two decisions will be made. We either reject the null hypothesis or we fail to reject the null hypothesis. And again, these concluding statements is the conclusion for the test. Those conclusions from the test will then bring us to our second conclusion where we take a look at, okay, if I rejected the null, that means the null is false and the alternative is true. And then I have to look at where I labeled the claim to see, do I believe or not believe the claim that's being made? Okay. So I love this chart as well. It's another slide that I highly recommend that you print out because you can clearly identify where the errors are. So error type 1 is if we reject the null hypothesis and then whoops, we found out it was true. My bad. And a type 2 error is if we failed to reject the null hypothesis, but we find out later that we should have rejected it because it was false. So an example of these errors, suppose Jeremy was in a car accident and a doctor in the emergency room believes he's dead. Jeremy's body has been sent to the mortician for preparation. Preparation in this context is euphemism for draining the blood out of his body and replacing it with fluids which retard deterioration, which means slowing it down. If Jeremy isn't dead when he gets to the mortician, he will be dead after he's prepared because he will not have blood in his body anymore. How should the mortician frame the hypothesis when he begins the work? Or really the question we want to ask is, which error is more critical in this, to be wrong? Which one's more dangerous in this situation? So let's say we let the null hypothesis be that Jeremy is dead, and the alternative is that Jeremy is alive. So a type 1 error, to have an error, you must make a mistake. So let's suppose the truth is that Jeremy is dead. Okay, so the null hypothesis, we failed to reject the null hypothesis. Jeremy is dead. He goes to the mortician, and we have a true null hypothesis, but the error is that we accidentally rejected it. We didn't know it was true. So we reject the null hypothesis, and that leaves us with the mortician to decide that Jeremy is alive. In order to have a type 1 error, you must reject this hypothesis. We just did that. In this case, the mortician believes Jeremy is alive, even though he's actually dead. What's the consequence? Well, there's really no consequence since Jeremy's already dead. So from Jeremy's vantage point, or the lack of it in this case, there's no problem, rest in peace. I mean, I would say the only problem would be is that his body would decay much faster because his blood was left in the body, and the customers would not be very happy when they're trying to have their funeral because the body won't be so pretty. Now, a type 2 error in this case is that we failed to reject the null hypothesis because we are considering the null to be true, which is that Jeremy's dead, and we find out later, oh my gosh, Jeremy's not dead, he's alive. So a type 2 error means failing to reject the null when it's false. If the null is false, then the alternative is true, meaning Jeremy is alive. Unfortunately, that's not that good news for long because the mortician thought he was dead, so he replaced his blood with fluids, and Jeremy now will die. So we can conclude that for the two errors, which one had a worse consequence? In this case, the type 2 was horrible because we killed Jeremy versus just preparing the already dead body. So the probability of a type 1 error is denoted by alpha, the Greek letter, and referred to as the level of the test, most commonly referred to as the significance level. And beta is the notation that we use to identify the probability of a type 2 error. Unfortunately, the value of beta depends on the actual value of the population parameter and thus cannot be determined unless the actual value is known, which is very rare. Okay, why not make both alpha and beta as small as possible? I mean, think about it. We're talking about error margins here. We want them to be small. But unfortunately, the probability of making a type 1 error alpha and the probability of making a type 2 error beta are inversely related. Thus, the smaller we make the probability of a type 1 error, the type 2 error probability grows, meaning it's more likely that a type 2 will happen, and vice versa. So in general, choose the largest level of alpha that is tolerable to avoid unnecessary increasing the probability of making a type 2 error. You really don't have to worry about that because alpha is all given to you, and the default for alpha is 0.05. So you should probably write that down, default 0.05. The null hypothesis is presumed to be true unless the sample data produces overwhelming evidence to the contrary. That is, the test statistic is calculated under the assumption that the null hypothesis is true. Sample data from a random sample are used to calculate said test statistic. The conclusion of a hypothesis test results in one of two decisions. You either reject or you fail to reject the null hypothesis, and then we'll follow that up with what does that mean for the claim as a secondary conclusion, which you will see when we run these hypothesis tests in future sections. So take note that we do not talk about accepting or not accepting the null. It's reject or fail to reject are two options for the test conclusions. There's no way to be absolutely certain your decision is correct, no matter which hypothesis is selected. Now, the steps in general, and again, our steps will be the same yet slightly different because we will be using our guru, but this is essentially what we need to do. We need to create the setup, so determine the null and the alternative hypothesis, which is what we practice today. Super, super important. Okay, specify the significance level alpha, the probability of a type 1 error occurring, which is 9 out of 10 times given to you in problems. Step 3 is to validate the assumptions of the test. Okay, remember these tests, from this point on, we are using the central limit theorem. So if it's the means, we have to see if the population is normally distributed or the sample size grabbed is larger than 30. If it's not, then the population needs to be normally distributed. And if we're talking about proportions, then we do the n times p and the n times 1 minus p and make sure both of those values come out to greater than 10. Then you calculate either the critical values or the p-value. There are two different methods that we are going to learn, the critical value method or the p-value method. As we move forward, p-value is much quicker and easier to use, but the problem with the p-value method is there is a large controversy on the p-value, and too much faith is being put into the p-value when it really, really shouldn't be the end all of a conclusion. But we will discuss what the heck a p-value is and the critical values and how they relate to this test in the future when we do the test. So the two methods we will choose from is a critical value method, which literally we draw a graph and we sketch out the rejection regions, and then we take the test statistic and we see where it falls. Does it fall in a failed to reject region or does it fall in a rejection region? For the p-value method, it is a comparison between the p-value and the alpha. And we have to do some calculations in order to find those critical values. And then we make a decision whether to reject or fail to reject. When we're working with a p-value, if the p-value is really small, smaller than alpha, we will reject the null hypothesis. If the p-value is very large or equal to alpha, we'll fail to reject the null hypothesis. And then we'll state the conclusion of the original question, which means that after we have the decision on rejecting or failing to reject the null, we look back at our hypotheses to which one was labeled the claim, which one's true or false, and then we start talking about whether we believe the claim that was made. And this concludes our introduction to hypothesis testing.